Today we're doing graphs of polynomial functions. Graphs of polynomial functions. So we're just kind of laying a ground layer, a basis for polynomial functions. Last week, so 5.2, that's going to be part of your upcoming test. Will be over section 5.2. And in section 5.2, the first part we talked about were the end behavior, the tails of polynomial functions. We know if the degree is even, both tails go the same direction. If the leading coefficient is positive, they go up. If the leading coefficient is negative, they go down. Do y'all remember learning that? Yeah. Okay. We also learned in section 5.2 about odd degree. They have opposite directions, right? If it's positive, they're going to go down on the left and up on the right. If it's negative, it's going to switch, and it'll be up on the right and down on the left. Wait. Up on the left, down on the right, right? Yep. Anyways, I'm looking at you trying to mirror that, and it's not going well for me. We also talked about local behavior. The degree tells us how many times the graph could do what? Cross the x-axis. So if your degree is n, your graph could cross the x-axis n number of times, at most. Now, it doesn't have to. We talked about the imaginary situation where we have imaginary roots, and maybe my parabola is floating above the x-axis and it never crosses. But the degree is still 2 because it could have crossed 2 times, right? What else does degree tell us? N minus 1 tells us what? How many turning points? How many turning points? Okay, so that should be a refresher on the 5.2 stuff. That stuff's coming back on your next test, okay? This starts 5.3. Recognizing characteristics of graphs of polynomial functions. So I wanted to start by looking at this figure 2, or figure 1. It says polynomial functions of degree 2 or more have graphs that do not have sharp corners. Do not have sharp corners. So on polynomial functions, they are always smooth curves. Always. Sharp corners are like what you see on what? Absolute value, right? Not here. Cusp. I told you the other word for this would be cusp, or sharp corner, or peak. These always have smooth curves. It says polynomial functions also display graphs that have no breaks. No breaks, ever. Okay? Curves with no breaks are called continuous. So these are continuous curves. What'd you say?
I was making a racing joke.
Oh, a racing joke. Okay. I thought you were saying that they had all real numbers as their domain.
If that's an answer, then yeah.
That's exactly what you're saying. Okay, they're continuous. They go on forever and ever in all directions. Okay, which leads me to exactly the point Mason was making. Domain is always all real numbers on polynomial functions. Always. Okay, so look at these two pictures. One of them is a polynomial, and one of them is not. Which one is and which one is not? One of these is a polynomial and one of them is not. The right one is not. Why not? It's a piecewise.
Plus, it wouldn't be smooth.
It breaks. It's not smooth. It breaks. It has some kind of gap. Some kind of, we'll learn later on, this is called a discontinuity. It's discontinuous. Okay? And so polynomial functions are always continuous. That's the way that they work. They always have domain all real numbers. Okay, so here's example 1. You don't have to write anything down. But if you were going to look at these pictures, and you've got, this one is F, G, H, and K. Which two are polynomial? The one on the left. So these two are polynomial, F and H. This one would be what? What's G? Absolute value. Good. And this guy right here, K, piecewise. Got a big old gap. Somewhere there's a problem. Makes it not polynomial. So do all polynomials have a domain of all real numbers? Yes. Yes. Every single time. So, whenever you're doing this and I tell you, state the domain and range. If it's polynomial, you're already given half the answer. Okay? You know it's all real numbers. Okay, so the next thing that we want to do here No, I don't want that one. Is example 2. Example 2. And it says f of x equals x squared minus 3x to the 4th plus 2x squared. And we're going to figure out a whole lot of stuff about this particular function, just given the function. Okay. It's not x squared. I lied. Fix this. It's not x squared. They would have combined those. It's x to the 6th. I lied. It's x to the 6th.
Oh, crap. You just said that.
Okay, so now that we've kind of established some things about these functions, we kind of have a feel for them. We know they're continuous. We know they have tails that do things. We know they cross the x-axis. We know that they also cross the y-axis because they're continuous. That means they don't skip any value in the domain. Okay? So if I first wanted to start off by finding the y-intercept, plug in 0 for x. Okay, so f of 0 would be 0. That's our y-intercept. Okay. So we know this guy crosses through the origin. Let's talk about the tails. What's the degree? Okay, so the degree is 6. Even degree, so that means that both tails are going to go either up or down. Is your leading coefficient positive or negative? Okay, so leading coefficient is positive. So what does that tell me? Both tails go up. Are we following so far? There is another point of interest that we can find using this function. What else could we find? Where it crosses the x-axis. Not only how many times, it could cross up to 6 times. But we also can tell where. Where exactly are those, what are they called? Roots, x-intercepts, zeros. All of those mean the same thing. What's one more name? Solutions. Good. Zeros or...
I pay attention sometimes.
You pay attention a lot. Solutions. I'll give it to you. I said a lot. And I meant that. How do we find it? How do we find those roots, solutions, x-intercepts? We set f of x, what? Equal to 0. And then we go to work. We've got different methods. We can factor. We'll look at some of the different ways we can factor in this lesson. What else could we do if it's not factorable and it's quadratic? Use a quadratic equation. Perfect. Okay, so we've got 0 is equal to x to the 6th minus 3x to the 4th plus 2x squared. And I'm already at a place where I don't know what to do. I don't know how to deal with a 6th degree polynomial. Factor out an x squared. Perfect. Factor out an x squared. So we're going to pull an x squared to the front. And we'll be left with, if I factor out x squared, that means I'm dividing x to the 6th by x squared. When I divide like bases, I subtract the powers. 6 minus 2 leaves me 4. Minus 3x squared, good, plus 2. Now, it's of quadratic form. It's not quadratic because it's an x to the 4th. But it is of quadratic form, meaning in this case we could do what? We can substitute a variable. What variable do you want? T. So we're going to let t equal x squared. So now this new equation is going to be t squared minus 3t plus 2. Everybody satisfied with this? You hate t? Well, we had 25 other choices. I guess we can pick one of yours next time. Does it factor now? Factors of 2 that make a negative 3. Negative 1 and negative 2. So t minus 2 and t minus 1. And now we need to go back to x. Remember, we can factor out and we can swap a variable just for ease of handling, but we shouldn't stay there. So now I've gone back to x squared minus 2 and x squared minus 1. Now what? You could solve them,
Oh, yes.
right? So each piece we've got to set equal to 0. The zero product property says that if the product of 3 factors is 0, then what? If the product of 3 factors is 0, then what do we know about at least one of the factors? It equals 0. So set each factor equal to 0 and solve for x. So if the first one is 0, x squared equals 0, what's x? X equals 0. There's one of our roots. We'll set the second one equal to 0. X squared minus 2 equals 0. Any ideas here? Swing the 2. X squared is equal to 2. So x must be plus or minus square root of 2. Right? It's x squared equals 2. So x is going to be plus or minus the square root of 2. Everybody okay with that one? Okay. Look at your last one. It's x squared minus 1. Anybody notice anything about that? Yeah, you can find the square root. I was hoping someone would say it's a difference of squares, but it doesn't matter. It's fine. It's a difference of squares. So if I square root 1, x is equal to plus or minus the square root of 1, which is 1. So we get 2 roots out of that. X equals positive 1 and x equals negative 1. So how many x-intercepts does this guy actually have? 5? 1, 2, right? In 0, that's 1, 2, 3, 4, 5. Are y'all seeing them? The plus and minus counts as 2. I'm sorry. Good? Okay, let's graph it. Are y'all ready for it? He's almost ready. Okay, so we're going to put all of this information in one place on this picture. What's the y-intercept? 0, 0. And what else do we know? We know it crosses the x-axis at -1 and at +1. And also at positive square root 2 and negative square root 2. Anybody know what those numbers are? Square root of 2? 1 point something. I agree. And we know that both of the tails go up. So in my mind, it's going to look something like this. Up, down. Hold on. It's going to go... Yeah, you're right. Yeah. So it's not going to actually go through at 0, 0. It just bounces and comes back up there. We're going to talk about why that is later on today. It's not because it is symmetrical. It is symmetrical, though. He said it's symmetrical on the y-axis. I think it is. I think this is an even function. I think we do see symmetry where it folds over the y-axis. Can you look at these zeros down here? You see x equals 1. You see x equals -1. You see x equals positive square root 2. X equals negative square root 2. But look right here. We had x squared equals 0. It's because that 0 had a degree of 2 that it bounces off of the y-axis or off of the x-axis right here. And it didn't actually go through the x-axis. It bounced off of it, kind of ricocheted. Can you see that? We're really going to dive into that later on today. All right, let's go on to example 3. Example 3. This time we have the same kind of setup. We've got f of x equals, and they give us 4 terms, x cubed minus 5x squared minus x plus 5. And they want us to find the zeros. Find the zeros. And a lot of times we'll have this move that we can make when we're trying to factor something with 4 terms. Okay, so out to the side, you should write this. 4 terms, question mark. Can you see them? There are 4 terms. If that's the case, a lot of times you can do what we call factor by grouping. You'll recognize it as soon as we start. A lot of times if there's 4 terms, you can factor by grouping. Okay? Factoring by grouping looks like this. Drop parentheses around your first 2 terms and your second 2 terms. Have you seen this before? So every time that we've busted up a quadratic and we've split that middle term into 2 terms, we've created a 4-term situation so that we can use factoring by grouping. Okay? We always start kind of in the middle of this process where we have to make those 2 terms. This one is already set up with 4 terms, so we can go right into it. Out of the first 2 terms, do you see anything that you could factor out? Pull out an x squared, and what's left? X minus 5. And on the second, what could you pull? Negative 1. Left with x minus 5. So, you see how it's negative x plus 5? We want it to match x minus 5. So if I pull a negative 1, I can change the sign on the x and on the 5. And now it's going to be x minus 5. So our 2 factors here are x squared minus 1 and... Anybody see the difference of 2 squares on the first? X squared and 1, they're both perfect squares. So that guy can split one step further. He can go x plus 1 and x minus 1 and x minus 5. So what does that mean about my zeros? Where are they going to be located? X equals negative 1, x equals positive 1, x equals 5. I'm going to plot those. X equals negative 1, x equals positive 1, x equals 5. How about a y-intercept? Do we have one of those anywhere? It's 5. How do you know, Joseph? If you plugged in a 0 for x, so if we were to go in here and evaluate f of 0, we would zero out the first term and the second term and the third term, and we'd be left with a 5 left over. Can you see it? Marcus, yes? This is a 0. 0 minus 0 minus 0 plus 5. So that means on my y-axis, got a y-intercept at 5. Talk to me about the tails here. It's odd.
So it would be down and up.
Down on the left side and up on the right side. Perfect. And so now can we kind of connect the dots here? It's a pretty rough sketch, more or less without knowing anything about where these turning points actually happen. But we can tell that it turns twice. It has to turn 2 times if it's going to go through these x-intercepts, right? How many x-intercepts does it have? It matches the degree this time. How many turning points? N minus 1. Any questions here? You could get more accurate with where these turning points actually occur by looking at a calculator. Okay, but without that kind of tool, this is the best we can do. How y'all doing? Tired? I know. Tomorrow's going to be worse. I'm going to be more tired tomorrow. That's how coming back from a holiday goes. It's always worse on the second day back. You think Monday's worse? We'll see. All right, here's example 4. Example 4, it says g of x equals x minus 2 squared times 2x plus 3. And our instructions here are find x and y intercepts. Okay, so to find the y-intercept, let's start there. To find our y-intercept, what are we going to do? G of 0, which means in my parentheses, I'm putting 0 for x.
Why did you separate the squared outside of it?
That is how it was written. So they're giving me these factors already in factored form. And I'm not having to go in and come up with these factors. This is called factored form as opposed to standard form, where it's like a strung out polynomial. These are factors that are already being multiplied by each other. Okay, so you already simplified in the first place. You had negative 2 squared is 4 times 3, which is good. So g of 0 is 12. That means I'm going to have a y-intercept at 0, 12. To find your x-intercepts, what do? Set it equal to 0, and then maybe you have to factor. Or maybe, if you're lucky, and they already set it up like this, you're already ready to go with your factors. So you can set each piece equal to 0 and solve for x. You see this x minus 2 business? It's x minus 2 squared. How do we lift the squared? How do we get rid of that? Square root both sides. It's not much of a move. What's the square root of 0? 0. So I'm going to have x minus 2 equals 0. So x is 2. There's one of my x-intercepts.
Wouldn't you have that twice?
Yeah. Yes. She said, wouldn't you have that twice? It's because there's a little 2 right here that's squared. And it looked like a no big deal because I was able to square root 0 on both sides, and it looked like it had no effect. The actual thing that it does is called multiplicity. Multiplicity. And actually what it does is it tells you what that 0 looks like. This one has a multiplicity of 2. Therefore, at x equals 2, your graph is going to bounce because it has an even multiplicity. Good question. Again, we're still not quite there yet in the notes, but y'all are onto it. You've got this thing figured out. How about the other one? We've got 2x plus 3 equals 0. Minus 3 on both sides. So 2x equals negative 3, divide by 2. So x is negative 3/2. Or if y'all are decimally, x equals negative 1.5. This one has a multiplicity of 1. Therefore, whenever it gets graphed, the graph's going to cross through here. It's going to cross through because it only occurs one time. Okay. All right, so if we were going to graph this one just really quickly, we can tell that at x equals 2, it's going to bounce. and at x equals negative 1.5, it's going to cross through. What's my degree on this one? 3. Degree would be 3 if I multiplied it all out. You've got x squared here, and you've got an x here. When you multiply it out, your degree is going to be 3. So it's odd. What's the leading coefficient going to be? Positive or negative? Positive. So we're odd positive. That means one tail is going to go down and one tail is going to go up. What was our y-intercept? 12? Golly gee willikers, that's a long way up there. Okay, so my graph is going to end up looking something like this. And what happens at 2? Good thing, because my tail should come back up somewhere. If it doesn't bounce right there, I'm in trouble, because I know it's not going to cross again. What are you thinking? Did we get it? You understand why it had to bounce? Because my tail has to be going up. And I only have that x-intercept. So it's allowed to touch and then reverb. Okay. All right, here's the last one. Do y'all have calculators with you today? Okay, we're going to get calculators in just a second. This is example 5. And it says h of x is equal to x cubed plus 4x squared plus x minus 6. And the first thing I want you to look at is how many terms does it have? It has 4 terms. So we could try factoring by grouping. But when I look at that, I don't have any common factors that I'm going to be able to pull out and make them the same. Can you tell? So factoring by grouping is a no-go here. So what else could we do? It's not quadratic. Factoring by grouping doesn't work. Your best bet at this point in your life is to grab a calculator and graph it and try to find your x-intercepts. Okay? So, okay. Okay, so I believe that this is kind of the picture that we come up with if we graph it. Would y'all agree with that? And so you're not able to factor to find your zeros, but we are able to graph it and see exactly where those occur. At -3, -2, and at 1. You could sketch it in your notes. But if all they wanted were the x-intercepts, you could say they're at x equals -3, x equals -2, and x equals 1. That should give you enough to get your homework done for today. Okay? That's the lesson. Tomorrow we'll have a short lesson. We'll grade your homework from today. And then Wednesday you'll have a work day. Are we good? Any questions today? No? All right, very well.